Hello everyone, hope you guys are doing well. This is our last mock exam for this year and I will be going over the solution for it. Please watch it carefully, pause whenever you like and go over it again. Make sure you understand all of the questions. Now that being said, let's get started. From the question 1. Now in here we're given a compound B-chlor 2. We don't know exactly what's the element B because they are asking us to find it. We're given the number of atoms, which is this many, and the mass of the substance is 111 gram. Now, as soon as you see this number, just divide it by Avogadro number to find the number of moles. So once we do this, we get that it is 3 moles over here. So we have 3 mole of atoms. Now, when you look at B-chlor 2, you can see that there is 1 B and 2 chlor in there, right? So that means 1 mole of B-chlor 2 has 3 mole of atoms. This is exactly what we have, right? We have 3 mole of atoms. That means we have 1 mole of B-chlor 2. Now, when you look at here, it says we have 1 mole of it is 101 grams. So this is the molar mass of it, right? And when you look at the periodic table, chlor, you would see atomic number 17 and 35.5 is the atomic mass. Now, this is what we want. And because we have 2 of them, molar mass of B-chlor 2 would be B plus 2 times 35.5 equals to 111. Now, 2 times 35.5 is 71, so B equals to 101. 111 minus 71, which is 40 gram per mole. And if you would check the periodic table, it is calcium with atomic mass 40. Atomic mass 40, atomic number 20. Now that's that. And the second question is your PA question. It says balance the first two equations in the given step 1 and step 2. Now, a lot of you are getting confused regarding the balancing. Let me tell you the easiest way. As soon as you see elements, we see that nitrogen has only one source in here from the reactant side. The same thing on the product side. Hydrogen, likewise, also coming from the one source, but oxygen, you see it's coming from two sources. That's why we will leave the oxygen to the last. Now, as you see, if we have the nitrogens the same, so nitrogens are okay for now. But we have 3 hydrogens and 2 hydrogens in here. So in order to make them equal, we just get the LCM of 2 and 3, which is 6. So we're going to multiply this side by 2 and this side by 3. Now we have hydrogens are good, nitrogens is not good, so we need to get the 2 in here as well to get the nitrogens. Okay. And as you see, so nitrogens and hydrogens are okay. And we're going to look at the oxygens. We have 2 from here and 3 from here. So altogether we have 5 oxygens. And we have 2 in here. So if let's say it was x, so 2 times x would equal to 5. X was equal to 5 over 2. So we know the coefficient over here is 5 over 2 to make both sides equal to 5. And you know that we can't have a fraction, so we're going to multiply everything by 2. So now this is, instead of 2, we will make it 4. Instead of 5 over half, we'll make it 5. Instead of 5 over 2, we'll make it 5. Instead of 2, we'll make it 4. Instead of 3, we'll make it 6. Now, in the second equation, as you see here, we have NO2 and then NO2. The only thing is off is the oxygen. So The easiest way would be if you would take one of the oxygen, you will have NO2 as you see, and we know that if we multiply everything by 2, we'll get rid of the fraction, which is what we should do. So I'm going to multiply everything by 2, it will be 2, this will be just 1, and this will be 2. And the step 3 is balanced. Now, it says calculate the volume of ammonia required at STP. So they're asking about ammonia here, and they're asking about how many liters of this we need. And they are telling us, what if you have 252 grams of this? So we need to work our way backwards. So we need to first, if you're going to see this, from NH3 we get NO, and that NO we use it over here, we get NO2, and then from NO2 we get HNO3. So we need to work our way backwards till we get to NH3, which is the ammonia. Now I'm not going to do the way that I did in our mock exam, because I feel like it confused a lot of you guys, so I'm going to keep it simple. So 252 grams of nitric acid. As soon as we know it, let's get the mole amount of that. Mole would be mass divided by molar mass. So we have 252 grams divided by 63, which is the HNO3 molar mass. So 63 gram per mole. Now over here we get 4 mole. So now you have from here that we have 4 mole of HNO3. Okay. Now we're gonna work our way backwards. So instead of 252, I'm gonna write here 4 mole. Now as you see from the balanced equation, so make sure you have the balanced equations. So 2 moles of HNO3 comes from 3 moles of NO2, right? So if you have 4 mole of HNO3, that means it would be what? We're gonna make it like this. So we're gonna write, we'll make cross multiplication like that, and this will give us 2x equals to 3 times 4, x equals to 6 mole. So we have here 6 mole of NO2. Now we're gonna put this 6 mole NO2 over here, and we would say that, okay, if 2 moles, as you see, because we have balanced, 2 moles of NO2 comes from 2 mole of NO2. If I have 6 mole of this, it will be also 6 mole, right? NO. Now we're going to put back this 6 mole NO over here. We're going to put the 6 mole over here, and then we say to ourselves, okay, I have here 4 moles of NO is made from 4 mole of HNO3, right? So 6 mole would be coming from the 6 mole again. So as you see, I worked my way up. I went from the back. I started from here. I said, okay, I found it 4 moles from 252 grams. I said that, okay, if I have 2 moles coming from 3 moles, from 4 moles I'll get X moles, which is 6 moles. And then I would put that 6 mole over here, and I would say that, okay, 2 mole coming from 2 mole, 6 mole, it would be 6 moles again. And then I would put that 6 moles over here to the NO that is made in the previous step. And then I would say, okay, 4 moles from here, and then 4 moles from that one, 6 moles will make it 6 moles. Now we found that we need NH3 mole is 6 mole. And STP, we know that mole times VSTP, which will be just you multiply it by 22.4, which is 134.4 liters, and that's it. But you need to write all the steps there, and that requires this. So the question in here, we have the 2B, so you need to write all the steps deliberately. You need to come from here. You say that, okay, 3 mole NO2 from the previous equation, and given you 2 mole HNO3, you would write here 4 mole HNO3, which is the amount you found from 252 grams. You would write here X mole NO2, and this is your step 3. So X you got here 6 mole. Now you're going to go to the step 2, and from here you said, okay, 2 mole NO2, 2 mole NO. So we're going to write the 2 mole NO, 2 mole NO2. If you have 6 mole NO2, which you found from here, it will be X mole NO, and X is just a 6 mole. And then you're going to go to the step 1, and then from here you would say, okay, 4 NO is coming from the 4 moles of NH3. If you have 6 mole of NO, it would be X mole of NH3. X would be just a 6 mole, and then V would be 6 times 22.4, and this is mole per, liter per mole. These are the units. Mole and mole cancels. You have 134.4 liters, and that's it. Okay, so that solves the question. The main portion in here is that you need to see which one. So I'm gonna delete this. You can get it from the video. So the main point in here is that you need to observe which one is getting used in the next step. So from here you get this one, and this one gets used in the second one, and this is the one connects to the third one, and this is the one. So you need to spot them and then make connections. Till you make this highlight, you're not going to be able to work this question, okay? And then of course you have to have a balanced equation. Now question 3, it's given a table. We have elements from group 17, 2, and 13. Group 17, we know it is 7A, group 2 is 2A, 13 is 3A. 3A group, we have given the electronegativities. It's asking for the dot cross diagram of the compounds formed between A and B and A and C. Okay, so that's what we need, A and B and A and C. Now I'm gonna tell you that the 7A group, because it has 7 valence electron, in order for it to complete octet, it needs 1 electron, so that's why the valency is 1. Valency is gonna be 1. For group 2, we have 2 valence electrons, so it needs to lose those 2 electrons to get the octet, so the valency is 2. For 3A, 3 valence electron needs to lose 3, so valency is 3. So we're gonna write it here. On top of the A, we're gonna write it 1. On top of the B, we will write 2. On top of the C, we will write 3. And then we're just gonna go cross and cross, so 2 will come here and 1 will come here, 3 will come here and 1 will come here. So from the electronegativity you can see that it is non-metal, and these are metals, right? That's why we write metals first, so it would be Ba2 and it would be Ca3. Basically these are your compounds. And we know that from the electronegativity difference is that between A and B it is electronegativity difference is 3, while with A and C it is also more than 1.8. It is 2.39, more than 1.8, so they are both ionically bonded compounds. So I'm gonna write here is Ba2 and then Ca3. These are our compounds. Now it is asking us to draw the dot cross diagram, so I'm gonna draw it here. The question, it is 3A. So 3A, so we have Ba2 and then Ca3. Now I'm gonna draw you both of them. So because with B we had 2 electrons, right? We had 2 electrons. So if you write the charge, it would be +2, and this is -1, and this is +3, and this is -1. Like the same as valency, but this time we have positive and negative. So meaning B lost both of its electrons. It became +2, and then A was here. It was like 1, 2, 3, 4, 5, 6, 7, and then it got across from the B, and then another A, the same idea, 1, 2, 3, 4, 5, 6, 7, and then 1 cross from the B, and this is -1, this is -1. Okay, so and then for Ca3 we have in here, I'm just gonna draw C in the center. So C lost all of the 3 electrons, and then A we have here 1, 2, 3, 4, 5, 6, 7, and then 1 got from C, and then 1 more A, 1, 2, 3, 4, 5, 6, 7, and then we got it 1 from C again, and then the last one we have in here A, 1, 2, 3, 4, 5, 6, 7, and 8, and then octet is complete, and these are your structures. Now we draw them in brackets, trying to show that these are ionically bonded. Now the next one, it is asking compare the melting points of both compounds in part B. So we have 2 compounds, Ba2 and Ca3. Now I'm going to tell you, because of the charge, we know that positive and negative, they are attracting each other. But when we have a +2 and then we have a -1, for example, they will attract each other even stronger, okay, stronger. And when you have +3 and then -1, they will do even more stronger. Okay, so the bigger the charge, the stronger the bonding will be, okay, the stronger. This is the ionic bond in here. The bigger the charge, since C has +3 charge compared to +2 charge of B, Ca3 will have higher melting point due to stronger attraction or stronger ionic bond. That is the answer. Okay, so that is that for question 3. Now we're moving into the question 4. It is asking us, there are lots of things going on in question 4. I'm gonna do this for you. Like, the main point of this video is that as soon as we do it, I want you to pause the video and do it for yourself, okay? Do not just watch it as a movie. You need to actively watch it, replay again certain stuff. So this is an active work, okay? So we have in here C2H4. It says indicate the number of sigma and pi bonds. Now if you remember from the dot cross diagram, we always have put the hydrogens to the ends and carbons are going to go to the center. So we're going to go with the carbon, and then we're carbon, and then they are both non-metals, so we have C2 and H4. We're going to make it in here carbon, carbon, hydrogen, 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 and hydrogen. We know that hydrogen is 1a group, so it brings one valence electron, while carbon is 4a group, so it will bring 4 valence electrons. And we need to get octet for both. So for hydrogen, I'm going to go with the cross. For carbon, I'm going to go with the dot. So in order to get the complete octet for hydrogen, as you know, all we need is to get 2 electrons in there. So one hydrogen brings itself, and the carbon shares one. Hydrogen brings itself, hydrogen shares one. Same thing here. So now we're finished with the hydrogens electrons, but we're left, as you see, with carbons electrons. So we use 2 of them. Now we still have 1 and 2 here left, and 1 and 2 here left for both. Now we know that we need to get a complete octet. That means in the circle, each circle of the carbon, we need to have 8 electrons. Currently, if you count it, we have here 1, 2, 3, 4, 5, 6 electrons. Now this doesn't work for us. That's why we're going to share it to make an electron, to make a bond. So each one will share, so we will do 1 and 2. Now let's count it again in the box. So we have 1, 2, 3, 4, 5, 6, 7. So octet is still not complete. So we're going to do one more. So once we do it, we will share one more electron to make a bond. So we're sharing both of them. So 1, 2, 3. So now you have it. So let's see. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now let's count this one. 1, 2, 3, 4, 5, 6, 7, 8. As you see, this carbon is octet complete and this carbon octet complete, and that's what we have. Now when you draw this, you're gonna just draw with carbon, 2 double bonds, double bond, and then you will have a hydrogen like this, hydrogen like that, and then like this and like that. Now this is Lewis diagram. Now this is dot cross. And then as you see, we have always the single bonds. They are the sigma, so 1, 2, 3. So we have 5 sigma, and then the last one is the pi. So we have 1 pi. Now it says indicate the bond angles hybridization. Now I have told you about this already. So when we have a carbon with 4 bonds, it is sp3. When I have carbon with 3 sigma bonds, so we have here 4 sigma. When I have carbon with 3 sigma bonds on it, it will be sp2. And then when I have carbon with 2 sigma bonds, it would be sp hybridization. And the shapes we have in here for sp3, it would be tetrahedral. For sp2, it is trigonal, not triangular, trigonal planar. And then for sp, it is going to be linear. And the bond for them, it'll be 180 degrees for this, 120 degrees for this, 109.5 for this. Now from here, as you see, we have 3 sigma bonds on this carbon, so it would be 1, 2, 3 sigma bonds. So this would be sp2 hybridization for both, and the shape is gonna be trigonal planar, and the bond angle is 120. So bond angle 120, hybridization sp2, molecular geometry, trigonal planar, I told you from the bottom. Indicate the names and draw the corresponding orbitals for the formation of each bond. Now we need to indicate the bonds that are formed in here. So as you see here, we have 1 sigma bond in here, right? And then 1 sigma bond. We know that hydrogen has only 1 s1, right? So this bond that is made in here, this sigma, is made from 1s of hydrogen, 1s of hydrogen and sp2 of carbon. And then this bond in here is made same way, 1s of hydrogen and sp2 of carbon. Now let me delete some of the stuff for you, because you have time to, while I was writing, you need to copy everything down. I'm gonna make some space for myself to be able to write this for you in a better way. Okay, so we have this Lewis diagram. So carbon, the only orbital that we have on the carbon. Now the reason it's asking in here, indicate the names corresponding orbitals for the formation of each bond. Now all these bonds, I have done this with you in the class, is that carbon has sp2 orbitals, and those orbitals looks like this. And then we know that s orbitals are just a ball. We have done this with you. And we know that p orbitals, they are looking like a dumbbell. Now, in here, the sigma bonds between the carbon and hydrogen, so the sigma bond that is made between carbon and hydrogen is made from 1s of hydrogen and carbon's sp2. And the way it's gonna look like, just the orbital of 1s, and then the way we will draw it, and this is sp2 of the carbon. Okay, and then all of them, they are the same. So these, all the four, they are the same. This 4, we mean this, and this. They are all the same. Now we have a center sigma in here, and there is also one pi, right? Now for sigma between the carbon and carbon, it would be made between sp2 of one carbon and sp2 of another carbon. And the way it will look is gonna be like this. And like this. And the other pi orbital in here, the one we have, the pi is gonna be just looking from here, the 2p of one carbon and the 2p of the other carbon, and they're gonna be just like this. So one and then the other one. If you remember, I have drawn you the picture of this like this in our class. You attach them here. This is the pi bond that we had. This time they're just asking you to write it. So if you remember, carbon had electronic configuration is 1s2, 2s2, and then 2p2, right? That 2p in here is the one that we have. So pi bonds, they are made between carbon and carbon. Now I want you to rewrite all of this stuff again for yourself, so I'm gonna draw the picture for you. So between the carbon and carbon, I have in here, so I have in here one, so between the carbon I have this one hybrid orbital, and I have another hybrid orbital in here. So this is one carbon and then one carbon, and then we also have, now in the question it didn't ask you to draw all of this. I'm just doing it for you to understand this, okay? it didn't ask for this. It only asked for you to do this. I'm just throwing you the picture so you would see it. So I have in here hydrogen and hydrogen. So 1s from the hydrogen here. So 1s from the hydrogen. And then same thing here, 1s from the hydrogen, and then 1s from the hydrogen here. And then we have a pi bonds, right? We have pi bonds, and they are made like this. So even though it looks like two pi bonds, it's just this two of them, they are just a one bond, just one pi bond, okay? And the bond in between them, this one is sigma. So I'm going to color the sigmas in blue. So this is the sigma, this is the sigma, this is one bond, the sigma, and the one with the pink is just the one pi bond. Okay, so this is not asking you to draw this, okay? Don't worry about it. The main thing what you need to do is that in here in the bonds is that hybrid orbitals, they always had this shape, okay? And then s orbital had a shape like this from the hydrogen, and the p orbitals, they had this. We have done this before. Now all you have to do is the carbon with the hydrogens and 1s of the hydrogen and sp2 of the carbon, because we figured out the hybridization, right? Now I will do the same for you for the carbon for C2H6. Now C2H6, if you will draw it, you will have two carbons in the center, so carbon and carbon. You have one hydrogen here, one hydrogen here, one hydrogen here, so one and then one, like this. So each hydrogen brings one electron, 1, 2, 3. Which one I choose for hydrogen here? Cross. So I'm gonna put the cross here, 1, 2, 3, 4, 5, 6. And then carbon shares one electron with each, 1, 2, 3, and it will share one in here. And this carbon will be 1, 2, 3, and it will share over here. As you see, we have octet complete, so 1, 1, 2, 3, 4, 5, 6, 7, 8. The same for this carbon, we have 8 complete octet. So the way it looks is that C, C, and then H, 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 and then H, H, H. You can just, if you want, you can draw this like that too, just doesn't matter. So now we have in here carbon with 4 bonds, right? So we're gonna look at the list that we told you before. Now I have erased it. I told you with 4 sigmas, carbon will have the hybridization of sp3. This is what it looks like. This is the dot cross diagram of it, and then the shape would be tetrahedral. Bond angle is 109.5, and the hybridization is sp3 for each carbon. Now the bond between them, this is a sigma, right? We only have sigmas in here. We have total of 3 plus 4, 7 sigmas. We don't have any pi, and so we know that the sigma between carbon and carbon will be made between sp3 and sp3. So they will all look the same, so this is the overlap for them. And then the bond between the carbon and hydrogen, because we have all of them the same, so we have 6. We have in here sigma made between the carbon and hydrogen, so it will be made between the sp3 of the carbon and 1s of the hydrogen, and this is the way it looks. So 1s of the hydrogen, and this is the sp3 of the carbon. Now I'll do one more for you for C2H2. So we have in here carbon and carbon, circle, circle, and we have just one hydrogen for each. That's the way it looks. And then I'm gonna put one electron for hydrogen. So one from carbon, one from carbon. So hydrogen is complete, only can take two. Now everything else, all these bonds, so I'll make this one with green for this carbon. So all the 3 electrons will be carbon will put in here to complete octet. Because if you check over here, we have 8 electrons. And if you check this one, we have 8 electrons as well. So altogether we will have, as you see, we have 6 electrons in here. So that means we have 3 bonds. The way it will look, C3 like this. Now we told you if the carbon has, now in here as you see we have 2 sigma bonds on the one carbon, so the hybridization of this carbon is sp, and the same thing in here is sp for this carbons. Now we have in here sigma, sigma over here, sigma, and we have pi and pi over here. So 3 sigma and 2 pi, right? And then we know that the sigmas in here made between the carbon and hydrogen is made between the sp of the carbon and 1s of the hydrogen. And the way it will look, it's just the same. So 1s and sp of the hydrogen. You need to write the names correctly to be able to get the points. So we have done this, and this is out. Now we need to do in here the sigma between the carbon and carbon. Now that would be sp and sp, and the way it will look just like that. So sp and sp of the carbon, and then we have in here pi and pi of the carbon, so they are just the same type but 2 of them. So pi between the carbon and carbon, and it would be 2 pi and then 2 pi of the carbons, and the way it will look like this, just a pi and another pi. Okay, so this is like a bond between them, the overlap. The same thing in here, the bond in here. Okay, so that's pretty much it about this question. Okay, now in question 5 we have in here the compounds. They are asking us to compare their volumes, but we're given their total mass. Now in here, as you see, the mass is the same for all of them, but we have these compounds and we need to get the volumes. In order to get the volume, we know that we need to multiply number of moles by the VSTP, right, which is 22.4 liters at STP. So that means in order to get the volume, we need to get the mole first. Now in order to get the mole, we know that we need to get it from the mass by molar mass, right? Molar mass. So as you see in here, the first thing we need to do is grab this mass divided by the molar mass, and we'll get the mole amount, right? And then we multiply that mole amount by 22.4 and we'll get the V. As you see, mass will give us the moles, and from moles we'll get the volume. This is the map. Now first of all, let's find the molar masses of these guys in here. C2H4, carbon is 12, hydrogen is 1. So if you do the math, it would be 24 plus 4, so 28 gram per mole. Now hydrochloric acid, it would be 36.5 gram per mole. And then BH3, if you do it, so it would be 13.8 gram per mole. So as you see, the one with the lowest mass is the BH3 in here. So we will divide these values in here for each one by their molar mass. So mole amount of C2H4 and C2H4 would be 100 divided by 28. And then for H-chlor, it would be 100 divided by 36 and a half. And then BH3 would be just 100 divided by 13.8. And then from there, we needed to multiply them by 22.4 liters. So in order to get the volume, so C2H4, V of C2H4 would be just 100 multiplied 22.4 divided by 28. V of C2H4, it would be 122.4 divided by 36.5. Sorry, this was hydrochloric acid. And then V of BH3, it would be just 100 multiplied 22.4 divided by 13.8. Now from the math, as you see, all the tops there are the same, right? So we need to look at the denominator. The denominator with the lowest value will be the biggest one, but with the highest number, it will be the smallest one. So we know that this is V1, this is V2, and V3. So V3 will be the biggest, and then we'll have V1, and then V2, which will be this case. Okay, so that is that. And then the next thing is about stating the molecular shape and bond angle of CH4 and all this stuff. Like, I'm going to teach you one way of doing it using the dot cross, and then I will show you Lewis diagram, but then I'm going to show you the easier way. Okay, so we have in here CH4. We know that the valence electrons of carbon is 4, hydrogen is 1, so 1 times 4, so altogether we have 4 plus 4, which is 8 electrons. So I'm going to do here carbon in the center, and then I have hydrogens in here. So hydrogen, I'll put the cross again. And then for carbon, I'll put a dot. 1, 2, 3, 4. Octet is complete for the carbon. The structure will look like this. Now you have 4 sigma bonds on carbon. That means it is sp3, and the shape is tetrahedral. Tetrahedral. Now I'm going to show you guys an easier way to do this. So easier way to do this is going to be like that. So we have in here carbon, right? So instead of hydrogen taken as 1, whenever you see hydrogen, count the number of electrons as 7, okay, for hydrogen. So if we have CH4, you have in here 4 plus 4 times 7, and then you have in here is 32 electrons. Now you will remember, whenever you have 32 electrons, it is tetrahedral, and then it is gonna be the hybridization is sp3, bond angle is 109.5. You just memorize this, okay? And then I will give you a couple of them that you need. You only need the linear, which is 16. You need a bent, which is 20, and you need trigonal planar, 24. So 16, 20, 24. So all you need to do is, so we have 24 electrons, 20 electrons, and 16 electrons. Now when you have 16 electrons, it is linear. Bond angle is 100, the hybridization is going to be sp. Bond angle is 180. Now when you have 20 electrons, it is going to be bent structure, and then hybridization in here is still sp3, and the bond angle would be in here as 107 degrees, I believe. 104 degrees, sorry. 104.5 degrees. Now when you have 24 electrons, you will have the structure is trigonal planar. Hybridization is sp2, and then bond angle is 120 degrees. 120. Okay, so this is the one that you need to memorize, just 4. Now let's look at the ones we have. In here we have H2O, right? Oxygen, group number 6, so valence electron is 6. Hydrogen, we said we take 7 for each, so it would be 2 times 7. So now we have 6 plus 14, which is 20. The structure would be looking, because it's 20 electron, we said it is what? Bent. So we have in here bent. So this one is tetrahedral. We already found it. Now NH3, nitrogen, if you look for the group number, it is 5, so it will be 5 plus 3 times 7, which is 26 electrons. Now I forgot to tell you about this one. Okay, I forgot to tell you about the one with 26 electrons. Let me do that too. So the one with 26 electrons, it would be called trigonal pyramidal. The bond, don't worry about the hybridization in here. Actually, in these structures, don't worry about the hybridization. All you need to know in here is their degrees and the names. So trigonal pyramidal is 107 degrees. So I'm gonna write them in the different colors so you could see. 109.5 for tetrahedral, 107 for trigonal pyramidal. Trigonal planar is 120. It's not obvious at all. So 120. 104.5 is for bent, 180 for linear, and the electrons are in here. So now let's write them in here. So CH4, we did the calculation with you. It is 32 electrons, is tetrahedral. 32 electrons. And then we have here H2O. H2O, we found it to be how many electrons? So in here we have oxygen. So oxygen is 6, hydrogen is 7 for each. So this is 20 electron. So this is in here is trigonal planar. Bent. And then we have here NH3. NH3 we have 5 plus 3 times 7. This is 26 electrons. As you see, it's trigonal pyramidal. The bond angle is 107. And then we have NH4 plus. So NH4 plus, we would do 5 plus 4 times 7. And then for plus, we're going to minus 1 electron. And this would be 5 plus 28 minus 1, and this will give you 32 electrons. Again, it is tetrahedral. And then, so we have aluminum chloride 3. So we have aluminum chloride 3 in here. So aluminum is third group, 3A, so valence electron is 3. Chlor is 7A group, so valence electron is 7, so 3 times 7. So this would be 24 electrons, and 24 electrons is trigonal planar. And then BH3, we have BH3, and then what else? CO2 and SO2, right? BH3, CO2, and SO2. Now boron, if you look at the group number, it is as aluminum, it's 3A group, so 3 plus 3 times 7 for hydrogen, so this would be 24 electrons again. So they are both trigonal planar. And then CO2, we have 4 for carbon, 6 for oxygen, 6 times 2, and this would be 12, 16 electrons. Now 16 electrons, if we look, it's linear, and then SO2 in here, it would be 6 for oxygen and 6 for sulfur, so 6 plus 6 times 2, which is 18 electrons, and 18 electrons, it is not given in here in this table. I'm gonna write that one as well. So 18 electrons is bent as well. So I'm just gonna write this one in here. Whenever you have 18 or 20 electrons, it is bent. Okay, just remember this. You will memorize this table and everything will be good in the exam. Now, as you see, I'm gonna color the same molecular shape. So 32 electrons, CH4 and NH4 plus, they have both tetrahedral. The ones with 24 electrons, they are both, oh, I forgot the same color. They are both trigonal planar. Okay, so 18 and 20, because we said they are both bent. So this would be bent in here, H2O. Should have colored the same. So 20 and 18, they are the same. They are both bent. Now, I'm running out of colors. Let me add one more. In here we have 16 electron for linear. And then I have in here 26 electron for trigonal pyramidal. Now, all you need to do is, if you're looking for the same shapes, calculate the number of electrons, and if they have the same number of electrons, that means they have the same shape. Now we're in question 7. It is talking about thermochemistry. So in here we have a reaction, and the enthalpy change is given to us. From the enthalpy change, we can see that it is exothermic. And in here we know that heat is released to outside. Now it's telling us, and we know that Q is just a positive number in here. Now, if we have this much heat released, how many grams of methane is burned? Now from here we can see that there is 1 mole of methane. We need to find the mass of this 1 mole of methane, which means you just find the molar mass. We know that the carbon is 12, hydrogen is 1, so 4 times 1. So we have 16 grams of CH4 given us 890 kilojoule of heat. So 16 grams of CH4, when it's burned, it gives us 890.4 kilojoule. It is positive. This is the Q we're talking about, the heat. It's telling us how many grams of methane will release 1780.8 kilojoule. If you would do cross and cross here, you would get X equals to 16 times 1780 over 8.8 divided 890.4, and this will give you 32 grams of methane. That's exactly the answer. Now, in the question 8, structure of ethanol and the provided bond energy, answer the following questions. Now, in your exam, you will be given the structures and you will given the table of the bond energies. You will use those to answer this question. Now, I will do it for you in here. So, question 8, we have C2H5OH plus O2 will give you CO2 and the water. Now I'm going to balance this for you. I have 2 carbons in here, so I'm going to put 2. I have 6 hydrogens here, so I put the 3. Now I have here 4 oxygens. I have 3 oxygens. Carbon and hydrogens are handled. So I have in here 7 oxygens, right? I know that it's coming from 1 mole of ethanol, so 1 oxygen is coming from here, so I'm left here with 6 oxygen coming from that side. So I need to put 3 over here to get the balanced equation. So now, since everything balanced, I'm gonna draw the structure. So we have in here C2H5OH. So these structures will be provided to you in the back of your exam paper, okay? So oxygen is always with a double bond. If you do the dot cross diagram, you will see it. We have 3 of them, and then carbon dioxide is like this. You need to know this. This is not given in the exam. And the water is like that. And then you have 3 of them. Now, delta H, this formula will be given, is the sum of the H broken, minus sum of the H formed, okay? Now, in here, the broken side is this side, okay? Because we need to break them, and we need to make this side which is formed, okay? So basically, reactant side minus the product side, bonds. Now I'm gonna add one more. So in here, let's count how many different type of bonds we have. So I have in here carbon with the hydrogens, and I have 5 of them, okay? From my balanced equation, I know that there's only 1 of them here, so it would be 5 times carbon and hydrogen. And then I have in here carbon with carbon, I have carbon with oxygen, I have oxygen and hydrogen. So I will do carbon with carbon, only 1. I have carbon with oxygen, 1, and I have oxygen and hydrogen is 1. I also have on the broken side 3 oxygen, so I'm gonna do 3 of the oxygen and oxygen bonds. Now I need to take the sum of this, okay? This is the broken. And the formed, I'm gonna write it here. So in the formed, we have it here. I'm gonna write the type. So as you see, I have 1 carbon and oxygen and 2 carbon. I have 2 bonds on 1 molecule, and I have 2 of them. So 2 times 2, I have altogether 4 of the carbon and oxygen, right? And then I have in here oxygen and hydrogen, so 2 of them, and there's 3 of them in here. So this means 3 times 2, which will mean 6 times OH. Now I need to minus them take the sum and minus them from each other. Now I'm gonna write them in here for you. So we have 413 for carbon and hydrogen, so 5 times that. So CC, it is 348, and then it would be CO is gonna be 358, and then I have OH is 4463, and then OO, it is 3 times 498, and then in here I have 4 times CO double bond, which is 799, and then 6 times OH is 6 times 463. Now if you do the sum of this stuff, you should approximately get like 4,718. Like it should be somewhere close into there. Like I used the ones, now I used the ones in here with 3, 4, 5, 4. I used a different table, but their values is almost the same, so 350. If you will use this one, and this is 464, everything else is the same. So this one is, sorry, this one is 741, and this is 464. Like this, using this values, you'll get 5,748. Now in the exam you will be given your own table. You're going to use it accordingly, okay? So don't memorize these values, just understand the logic. So now you're going to do delta H 4,718 minus 5,748 This is negative 1030 kilojoule per mole. Now that's what you get, right? And you can see that it is an exothermic reaction as it was supposed to be. Okay, so this is the one you have, and then so it's the theoretical enthalpy change, which we will use in the question after. So I'm just gonna switch to that question right away so we can get this one done. So question 11, I will come back to the question 9 and 10 after. So it's literally our lab in here. So we're given a lab that investigates the combustion of ethanol, and then we're going to use the specific heat capacity of the water is 4.18 joule per gram degree Celsius. It says that considering that 200 milliliter of water is heated exactly by 20 degrees, so we know that delta T is 20 degrees Celsius. 200 milliliters of water, we know that the density of the water is 1 gram per milliliters. So the mass of the water is just the 200 grams, right? If you multiply this by that, you will get 200 grams. Now it says you to indicate what type of system is this: open, closed, isolated. Calculate the heat released during the process. Now let me do the heat and I will answer the A. We know that the heat equals to Q equals to MC delta T. We know that we had 200 grams of water, and then it is 4.18 joule over gram times degrees Celsius multiplied by 20 degrees Celsius. If you will do the calculation, you need to be getting from here 8,360. Sorry, just 2 times of that. Your answer should be 16,720 joule, because we know that gram cancels gram, degrees Celsius cancel that, so it would be 16.72 kilojoule, right? If I will divide it by 1,000, 16.72 kilojoules. Now in this case we have used how much ethanol? Let's figure that out. I have 395.2, and this is how much ethanol was used. If you will minus this from each other, you would get 1.3 gram of ethanol was used, right? Now, number of moles of ethanol burned, we know that we can find the molar mass of ethanol. It will be, we have 2 carbons, so 12 times 2. We have 6 hydrogens, so 6 oxygen is 16, it is 46 gram per mole. Now, number of moles, it would be 1.3 divided by 46, and now this will give you the number of moles, which is 0.0282. 283 actually. I want you to do the calculation with me, so all of this stuff, mole. Now it's asking you to find the experimental value for delta H. Now from here we got the Q, right? Now let's write it for ourselves. So we know that 0.0283 mole gave us the kilojoule was 16.72 kilojoules, right? 16.72, so this positive kilojoules, this is the Q. Now we want to find it for 1 mole. This would be X kilojoule. Now X would be just 16.72 divided by 0.0283. Now let me do the calculation too. This will be 591.6, which is 592 kilojoule. Now we got our kilojoule, 592 kilojoule per mole. In terms of delta H, this value, it is negative 592 kilojoule, because we know that they have opposite signs, right? So this is negative 592 kilojoule per mole. Now the theoretical one we calculated from the previous equation was negative 1030 using the bond energies, right? Now this part is done. I'm gonna do, so show the calculation of enthalpy change for 1 mole of ethanol. This is the one for 1 mole of ethanol. We did this one too. So this is the D. Now calculate the percentage error. Now I'm gonna do the F and I will do the G. So in the F we have in here is, so we know the percentage error equals to theoretical minus experimental divided by theoretical multiplied by 100%. That was the one. But everything in module, right? So we know that our theoretical value is negative 1030. And then we minus from minus 592, this is the experimental, divided by negative 592. Now module here multiplied by 100. Now in here we have negative 1030 plus 592 in the module, divided by just a positive 592 by 100. Now if you will do this, 538 divided by 592 multiplied by 100%, it is approximately 74%. Okay, now that is the F we did. It says what source of error could lead to inaccuracies in your results. Now in here we had, if you remember in our experiment, we had the lab set up. We were burning the alcohol from the alcohol lamp and we're temperature recording it, right, with the stand and everything. Now in our case, because the heat was going out, we were trying to heat the water in here inside, but some of the heat was actually escaping to outside, right? Some of the heat was going outside, going to outside. So there was a heat lost to environment. You can also feel it, right? When we were heating it, when we were close to this container, we could also feel the heat. That's because some of the heat was actually going towards us. Not all of the heat was going there. And that's why we got an error. Also, the other thing that we forgot to take into account is that the copper metal that we had over there, it also required heat to be absorbed, right? So some of the heat lost to copper container. So we couldn't heat the water without heating the copper, right? So we still lost some of the energy to copper as well. So that was the reason of our inaccuracies. So that one is done as well. Now it says to, in the A portion, is I indicate what type of system is this. Now in our system, as you remember, we didn't have a lid, right? There was no lid. It wasn't a lid. We know that water can come out from here. It can boil as a bubbles. It can come out. So this was an open system. Now you guys need to remember, if we have a system where we would close it, so there won't be no matter transfer. So matter transfer won't happen, but energy transfer can happen. That is a closed system, closed. When there was a no matter, no energy transfer, that is an isolated system. You need to review your notes. So in our case, it was an open system. Now that one is done as well. It says in the question part C that in another lab, 50 grams of unknown liquid heated by 20 degrees, the same amount of heat is absorbed by the liquid. So the heat it's absorbed is this, right? So this is the heat we found. same heat. Now it's saying us that this is a 50 grams. It is a 50 grams and 20 degrees Celsius. Calculate the specific heat of the unknown liquid. Now we know that Q equals to MC delta T equals to 16,720 joule, right? We know that the mass is 50 grams. C is C. Delta T is 20 degrees Celsius. 16,720 joule. Now C would be 16,720 divided by 15 times 20, and this is basically dividing it by 1,000, 16.72 joule over gram times degree Celsius. This is the specific heat they are talking about. Okay, so this one is done as well. Now in question 9, we need to talk about the intermolecular forces. Now before we go into the intermolecular forces, I'm going to go quickly over them. Intermolecular forces were 3 of them: London dispersion, and then we had in here dipole, and then we had hydrogen bonding. Now London dispersion had to do with molar mass. For example, if we want to compare H2 with N2, we know that the molar mass of N2 is higher, so the London dispersion is going to be higher in N2. Now dipole forces, let's compare. It has to do with polarity of the bonds. Polarity of bonds. Now if I have in my hands CH4, and then let's say we have carbon and hydrogen, and then I have hydrogen chloride, or hydrogen, let's say fluoride. Now in CH4, we know that the bond between carbon and hydrogen, and we have a bond in here between fluorine and hydrogen. Now we know that electronegativity increases from left to right, bottom to top. Now hydrogen is here, carbon is here, fluorine is here. Now the difference between the hydrogen and fluorine and between the carbon and hydrogen, we know that the difference in here, the electronegativity difference, will be lower, and in here the electronegativity difference will be higher, which is why the dipole force in here would be the bigger, so in hydrogen fluoride. So for the polarity, you need to have more than one element, right? We know that, for example, H2 is not polar, so H2 only has London dispersion force, no dipole, okay? Because H2, there is no polarity, non-polar, right? Non-polar molecule. Now for hydrogen bonding, we told you about this, NOF. So we need to have a bond between nitrogen and oxygen, oxygen and hydrogen, and fluorine and hydrogen. And whenever you see these bonds happening, you know that you have a hydrogen bonding. Now, and when you put them on a scale, LD is the weakest, dipole is the stronger than that, and hydrogen bonding is way stronger than both of them. Okay? So that's what we have. Now in here it says identify the strongest intermolecular forces of attraction in the following substances. Now in here you have OH, NH2, if you remember NOF. We know that right away in here the strongest intermolecular force for this one is hydrogen bonding, and hydrogen bonding for this one. Now we have in here N2 and xenon. We know that in here they are just made by themselves, so all they have is London dispersion. Now keep that in mind, that every single element, every single compound has a London dispersion force. So in here, because they are only made by themselves, it's non-polar, so we don't have a dipole, so all we have is a London dispersion. And in P-chlor3, as you see, we have phosphor and chloride. Now there is an electronegativity difference between them, so this one will have a dipole. That's the strongest, right? It has. Even though it has LD, we don't mention it because we only look for the strongest one it has. It doesn't have a hydrogen bonding, and that's what we have for the answer. Now it says compare the boiling points of xenon and p-chlor3. Now in here, because we know that xenon only has LD and this one has dipole-dipole force, right away we know that p-chlor3 will have a higher boiling point, because the stronger the intermolecular force, so stronger IMF means higher melting point and boiling point. That means that like two molecules, they are attracting each other stronger, like p-chlor3, like millions of them in there, they are attracting each other more, so it's hard to break them apart. That's why their melting point and boiling point will be higher. Now in here, when you compare the two, now in this case we both have in here is hydrogen bonding, so it's hard for us to decide. And then in that case we're gonna look into their molar mass. Now in here, the molar mass of this is that this part is, we have 2 carbons, 5 hydrogens, 7 hydrogens. 2 carbons is 24, and we have 7 hydrogens, 7, and then 1 nitrogen is 14, so altogether the mass is 31 plus 14, 45. Now in here we have 3 carbons, 36 plus 7 plus 16 and plus 1, now 36 plus 24, which is 60. Now as you see, they both have a hydrogen bonding, but because C3H7 has a higher molar mass, it has a stronger London dispersion. That's why C3H7OH will have a higher boiling point, okay, melting point as well. Now it says compare the dipole-dipole forces of N2CH3NH2 CH3CH2OH. Now in here, N2 is not polar, so it doesn't have there is no dipole-dipole force in here. Now we have here CH3, like we have with the NH2 and OH, they both have a hydrogen bonding. Now if you will look at it's asking about dipole-dipole forces. Now if you will look at the periodic table, you would see that nitrogen, oxygen, and fluorine are located like this, and the hydrogen is here. As you see in here, nitrogen is closer to hydrogen, but the oxygen is one away. So oxygen and hydrogen electronegativity difference will be higher than the electronegativity difference of nitrogen and hydrogen, because nitrogen has a lower electronegativity, and that's why CH3OH will have the highest dipole-dipole. This one will be the second, and this one doesn't have any dipole-dipole, so we'll put it in the third place. So that is that, guys. You need to review all of this stuff. And then in the question 10, it is talking about the metallic bonding. It says which metal is liquid at normal temperature and pressure. This is the mercury. Mercury, the one in the thermometer, you already know it. It says what's the chemical symbol? It's Hg. Which two metals can melt when held in your hand? You need to look at your notes. It's like cesium and gallium. And what are their chemical symbols? That's they are. It's what's the melting point of tungsten? I think it's about 2,800 something. You need to check it for yourself for sure. Okay, so it's around 2000s, I believe. And then it's asking list the factors that contribute to magnesium's higher melting point compared to sodium. Now that is a good question. If you guys remember, is that metallic bonding. I'm sorry, I missed it with another metal. So tungsten melting point, it is 3,422 degrees Celsius. Now about listing the factors that contribute to the magnesium higher melting point than compared to sodium. Now, metallic bond was happening due to free electrons of metals. For example, if I had a metal, let's say magnesium, there would be two electrons floating around, right? Electron floating around, and many magnesium ions in here. So this would be my metal. Now on the other case, I have a sodium in here, so sodium ion, positive ion, and then one electron. Sodium plus ion, one electron, right? So as you see, the one that has higher charge has more free electrons, and when you have more free electrons, if you remember from the previous question, they will attract stronger to each other. That's why it will be hard to break down this metal. So the higher the charge, so the higher charge, it means more free electrons. That's why higher melting point. That's why magnesium melting point will be higher than melting point of sodium, because the charge of magnesium would be +2, there would be 2 electrons, and then sodium would be +1, and there would be just a 1 electron moving around. So that is the answers in here, guys. Okay, now the question about the last one in here, it says define the physical properties of covalent network structures, give examples of substances which possess. Now covalent network structures, they are super strong. Like one of them is like a diamond, is the one that has covalent network structure, which is why diamond is so expensive, and it's really hard to break it. Now I want you to Google about this and find all the structures that have covalent network structures. One of them is like copper, the other, carbon is the one like in diamond, and we also have like sulfur, and then also there is like a boron, phosphor, silicon. So all these elements, they form like a covalent network structures, which is why they have a very high melting point, and they are very hard. Okay, for example, they make a compound like silicon oxide, silicium oxide. Silicium oxide is like the main material of the glass, but they can make like a super strong glasses out of this one. So covalent network structure is the last question, guys. I'm gonna make this video ready. Hopefully I will post it. Wish you guys good luck in the final exam.